Robust printer is basically Lego Boost plotter that writes block letters with a pen. The important part is that it doesn't rely on fixed library or letter shapes packed into the code. When you type a word or on your computer, AI works out how to draw each letter from scratch. The strokes, pen lifts, and how the paper and carriage need to move. After each character, it leaves a little space, then moves on to the next one. So the whole word reads left to right in uppercase like a tiny printer. It's physical Lego doing the drawing, but the how do I print this letter part is AI all the way. No hard-coded templates. When you ask it to print something, the host doesn't just send a few commands. It builds full MicroPython program for the Pybricks hub from what the AI returns with every pen lift and motor movement spelled out in code. You could open that generated script and rewrite it by hand, but even for a short word, it's a lot of steps to get right, and one small mistake throws off the whole layout. That's why the project assumes you will let AI generate the print program. So this is the printer which I assembled using Lego pieces. So it provides stable foundation for the entire printer, ensuring that all the components stay aligned during operation. A rigid base is important because it reduces unwanted movement and vibrations, helping the printer produce more accurate and consistent drawings. All the other mechanical parts, including the motors, carriage, and paper feed, are mounted on this base. The printer is driven by three motors, each responsible for different movement. Motor A. So motor A feeds the paper backward and forward, allowing the printer to position the paper accurately for each line and character. This is motor B. Motor B controls the pen by lifting it off the paper and lowering it when drawing is required, ensuring that marks are made only at the correct locations. An external motor connected to port D moves the print carriage horizontally across the paper, positioning the pen precisely from left to right. By coordinating the movements of these three motors, the printer can accurately draw letters on the paper. When generating MicroPython code, we use the command pattern in Python. However, instead of creating command objects, we pass simple data structures because the Lego Boost app has very limited memory. This approach reduces memory usage while still following the same command pattern concept. Each command is represented as data, which is later converted into the corresponding MicroPython code. Later, we will disassemble the external motor assembly and examine the structure in detail. We will learn how the gears are connected, understand the gear rotation, understand the gear ratios, and how motion is transmitted, and explore the design of the pen holder mechanism. This will help us understand how each mechanical component works together to produce precise movement and accurate drawings. To order Lego compatible markers, which I will use instead of regular pen. They are much more convenient for drawing because they are designed to fit securely into Lego builds, making them easier to mount and providing more consistent result. I have built Lego Boost applications and used Pybricks and AI to program the robots. I won't go into details this time, but we will still debug the application and understand how it works. If you'd like to get into the details, you can watch the videos I'll include in the description. Let's print. Lego printed. Oh, oh, oh. When you run the host application, it prompts you for a word, supported letters only. So it has something like hello or help. The app sends that word to the AI with prompts, print request txt as the system prompt. The file is the drawing specification, coordinate system, angle grid, font rules, and exact stroke sequences for each supported letter. From that, it writes output print JSON, the uppercase word, one section per letter, in order and short reply. Each section has the letter comment describing the stroke plan on the command list. Commands are just type and angle only. Each command in JSON has two fields. Type, it's like pen down, pen up, carriage right, carriage left, paper forward or paper back. An angle is a number from the prompt grid, like 30 for the pen, 253 for full width, 100 for full height, and etc. or special carriage steps. This JSON doesn't contain distance or physical units. The plan layer uses angles only, as defined in print request txt file. Travel distance is not in print JSON. The host maps those prompt angles to have variables like long t, short a, half t, spacing a, and etc. using calibration like paper fit, carriage gearing, letter size assumptions, which we will explore. So JSON is about angles from the prompt. Distance is computed later from angles plus calibration when the hub script is generated and run. So this template adds host-only steps that JSON must not include. For example, letter start, letter end, letter pen up, repositioning, carriage on the gap between letters, as described in the host runtime in print request txt. Now, after the JSON is generated for the word, we answer deploy to the hub and run with yes. You should also note that under the generated folder, print Python file is generated based on the output print JSON file and the template print Python file. The host reads template print Python file, which is the complete hub program containing the motor setup, speeds, and functions responsible for executing each operation. Only one part of the template changes for each print. The block between host program start and host program end. Inside the block, the host generates default word on the program list, which we will explore later. The generated block replaces the existing content between host program using the commands from output print JSON. Everything above and below those markers, such as motor initialization, run, and run program, remains unchanged for that template. So the generated print Python is the Python program uploaded to the Lego hub for execution. The file is then the complete MicroPython program that is uploaded to the Lego hub and execute it. You can compare the template print Python and the generated print Python files. You will see now the printer running, but I removed the pen so you will only see the mechanisms in motion rather than the actual printing. So typing yes or Y. The motor B controls the pen by lifting it off the paper and lowering it when drawing is required, ensuring that marks are made only at the correct locations. So the pen angle is 30 degrees, which we'll see later why it's set to 30 degrees. You can see that the panel that moves the marker up and down. On the back of the panel is a Lego piece that serves two purposes. It's the orange one. First, it limits how far the panel can move upward. Second, it presses against the marker guide, allowing the motor to raise and lower the marker. The marker guide keeps the marker aligned while allowing it to move up and down. The 30-degree motor rotation is calibrated so that the panel moves just enough to hit the stopper. It prevents the mechanism from applying excessive force, which could damage the pen structure or Lego components. We also have pen stabilizer. It prevents the pen panel from rotating or moving when the external motor moves the marker horizontally. This keeps the pen mechanism stable and ensures that the marker maintains the correct position while drawing. So the bottom position of the pen is calibrated so that it reaches exactly the paper level. When the pen is lowered to this position, it makes contact with the paper and is able to draw without applying excessive pressure. Let's test it. Motor A feeds the paper backward and forward, allowing the printer to position the paper accurately for each line and character. When printing letters, I want each vertical stroke to be 10 mm high. For motor A, we don't know the exact gear ratio between the motor rotation angle and the paper movement. Therefore, we calibrate it by measuring how many motor degrees are needed to move the paper a known distance. In this case, the calibration ensures that each vertical stroke is printed as 10 millimeters. In this code, we have some variables such as letter short mm, paper, whole dig, paper call mm, half, and we also have paper dig function. To make it easier to explain, I asked ChatGPT to generate and explain it so we can go through together. So the goal is to make each vertical stroke exactly 1 centimeter long. This paper dig 150 and paper column 35 are physical calibration test values obtained by measuring how many degrees motor A rotates to move the paper a known distance. I did this myself by rotating the motor 150 degrees and measuring that it produced 35 millimeter line. Now we have a formula that calculates degree per millimeter paper. So why do we use half here, which is defined as paper call divided by 2. This is integer division or floor division, which divides the numbers and rounds the result down to the nearest whole number. The addition of half is classic programming trick used to perform integer division with rounding instead of standard integer division truncation, which always rounds down. By adding half of the divisor before dividing, any decimal value of 0.5 or higher is bumped up to the next whole number for accurate rounding using the integer math, which is essential because LEGO Boost environments cannot work with float numbers. For example, without it, a result like 4.7 would incorrectly truncate to 4, whereas adding half of the divisor correctly rounds it up to 5. So degrees per millimeter is so degrees per millimeter equals 150 divided by 35, which equals 4.28 degrees per millimeter. So the program assumes that 1 millimeter is about 4 degrees, but the program approximates 1 millimeter of paper movement requires about 4 degrees of motor eye rotation. The actual measured value is about 4.28, but the formula uses integer division, so it rounds down to 4. So the program calculates that 10 millimeter paper movement requires approximately 43 degree of motor eye rotation. And the important point is that the code doesn't know the physical paper size. It only knows the relationship Before diving into the numbers and explaining how the external motor moves horizontally, I would like you to see it in action. I will print the letter without the pen so you can see how the external motor moves. Note that the final position is limited by the maximum rotation of the last gear. If the gear rotates beyond this point, it can damage or detach the Lego construction. You will see that it never goes beyond this limit. As you saw previously, each vertical stroke of the letter is 1 centimeter high. And we want the total letter length to be 25 millimeters. In the code you see that we have letter length mm, dig per carriage, carriage gears, and carriage dig function. To explain the external motor movement, gear ratios, and how everything works, let's do it with ChatGPT. So the external motor controls the horizontal movement of the pen carriage. The motor doesn't directly move the pen by measured distance. Instead, it rotates gears that moves the carriage along the track. I will disassemble the external motor later gear assemble it so we can take a closer look at it. So the 8-tooth gear on the motor meshes with the 12-tooth gear on the carriage side. First we measure how many motor degrees are required to move the carriage by 1 millimeter. So the value so this value is obtained through calibration by testing the actual movement. During calibration, motor D was rotated by 200 degrees and the carriage moved by 10 millimeters. So the degrees per millimeter of carriage movement are calculated by dividing the motor rotation by the carriage movement. So that means that the motor must rotate 20 degrees to move the carriage by 1 millimeter. So this is the mechanical calibration of the external motor system. But the external motor has gear configuration defined by carriage gears 812. This means that an 8-tooth gear is mounted on the motor side and 12-tooth gear is mounted on the carriage side. So the gear ratio is calculated by dividing the carriage side gear teeth by the motor side gear teeth. So the larger 12-tooth gear rotates slower than the motor gear, so the motor rotation must be converted through the ratio. From the carriage home position to the maximum safe right position, the carriage moves 19 millimeters. We measured it. This is a linear distance, not gear rotation. The next step is to convert the carriage distance into the required motor gear rotation. So the carriage dig function calculates how many degrees motor D needs to rotate to move the carriage by a given distance. It takes the carriage movement in millimeters, multiplies it by the calibrated value of 20 degrees per millimeter, and then applies the gear ratio between the motor gear and the carriage gear. For the maximum carriage stroke, the calculation is 253 degrees. This measures that the motor D rotates approximately 253 degrees to move the carriage from the left-hand position to the right limit. But, but the carriage movement isn't exactly the same as the printed line length because the pen is mounted away from the carriage reference point. So the pen offset must be considered when measuring the final printed letter size. With its assembled the external motor, you can see that the 8-tooth gear is directly connected to the motor shaft, while two 12-tooth carriage gears are connected to it. It doesn't matter whether we use one or two 12-tooth carriage gears. The number of 12-tooth gears doesn't affect the calculation we perform. The calculation only depends on the gear ratio between the 8-tooth motor gear and the 12-tooth driven gear. You can see that in the project I have a letters folder containing the letters that we support. When I created the project, I really wanted to make sure that each letter was printed correctly. What I did was ask the AI to generate the letter code based on the prompts we already had. It appeared that in some cases the letters were not run correctly because of the initial prompts and the way the letters were supposed to be printed. I asked the AI to fix those issues and also update the prompt file. After that, everything went well. This is the way to test letters is through the Pybricks code. I copy letters code here and run it. I will show how to do it without paper. Let's copy the S letter code and deploy it to the hub using Pybricks code. Let's debug the application. We input a word and passing that to the handle prompt. So the handle prompt, in the handle prompt we call generate. So the AH will return validated print intent containing the normalized user word, the model sections, and the reply message. Then we save it in print.json file. The prepare letter print run. In prepare letter print run, we build the hub-ready print Python file. So we generate the file inside generated dir by inserting intents letter program into the template. The function then returns the path to the generated file. Then connect up with scan Bluetooth for the Pybricks hub with optional name and timeout, and connect over Bluetooth and return the hub object or none if nothing is found. So then we deploy it by stopping any running hub program first.